Hi everybody! So in today's video we're going to spend our first of several days talking about ways that we can use linear equations, which we've been learning about in this chapter, to apply them in a real world problem. So this is where we start to see how will you ever use this in the real world? And we're going to start with some pretty basic examples today, and we're going to build up to some real world experiments later on in this chapter. So let's take a look here. A linear equation is any equation whose graph is a line. So if the graph looks like a line, we call it a linear equation. When we write a linear equation for a real world problem, we call it a linear model. Now you may have heard the word model before, as in model airplane. What it basically means is that we're using this to represent mathematically something that happens in the real world. Just like a model airplane is a smaller version of something that exists in the real world, a linear model is a mathematical version of something that exists in the real world. An example of a linear model would look like this. Y equals 3x minus 5. Now, in the linear model, the slope is the thing that repeats. It is something that occurs over and over again, and a lot of times we call this the rate. So let's say, for example, you were looking at how much money your company earns, and you knew that you earned $10 per day. This number, that $10 or $3 or $7 that you earn every hour, would be the thing that repeats. The number at the end, the y-intercept, is a one-time amount. So it might be an amount you need to spend one time to purchase supplies for your company. You don't necessarily need to purchase those supplies every day. You might purchase them one time that lasts you the whole month. So it's something that is a one-time amount. Let's take a look at an example. When we write linear models, there's always going to be two steps to our process. The first step is going to be to define our variables. So tell me what the letters in your equation stand for in the real world. And so the second step is going to be to actually write the equation that has those letters in it. For today, we're simply going to work on writing these equations based on a story problem. So let's read this together. It says a truck rental company rents a moving truck for one day by charging $29 plus 20 cents per mile. Write a linear model that relates the cost, C, in dollars, of renting the truck to the number of X miles driven. When we read a problem like this, sometimes it's going to tell us in the problem what variables to use to stand for which pieces of the problem. So it says here, the cost, C, in dollars. That's going to be our first variable. So where it says define our variables, we're going to write that C equals the cost in dollars. It is very important to define your variables carefully. So not just it stands for the cost, but what do we measure cost in? Is it dollars? Is it millions of dollars? It could be thousands of dollars. We want to know what that really means in the real world. Now the second variable that it gives me here is the number of X miles driven. So X is going to stand for the number of miles driven. Oh, I can't spell. D-R-I. There we go. Driven. There we go. All right, now once we have our variables defined, we need to look for two numbers in our problem. The one that repeats and the one that is a one-time amount. So, if I look at this problem again, I see that there are two numbers at the beginning. It says we rent a truck for one day by charging $29 plus 20 cents per mile. Now the $29 is only being charged once, but you're going to charge the 20 cents every time you drive an extra mile. So that tells me that the 20 cents is the repeater. The other thing I know is that the $29 is a one-time thing. So I go to the counter at the truck rental place, I give him $29, I drive for a while, I come back, and I have to pay an additional 20 cents for every mile that I drove. So now let's see if we can set up the equation. C is going to stand for the cost that I have to pay total. Now the repeater number is like the slope, it's the rate. So this 20 cents would go next. And because I'm going to pay that 20 cents for every mile, and X is the number of miles, I'm going to multiply that number by X. Those two are going to be connected. The one-time amount, the $29, is going to go last because I'm only going to pay that one time. And that's why it doesn't have an X. It doesn't repeat every mile. It's just a one-time deal. And that's it. That's how you set it up. Let's take a look at problem number 2. A chemist's salary was $35,000 in 1985 and increased by $300 per year. Write a linear model that relates the salary S of the chemist to the number of years since 1985. Now in the previous problem, they told us what two variables to use. In this problem, they only told us one variable to use. So it says here, we want to relate the salary S of the chemist to the number of years since 1985. They specifically told us S should be the salary of the chemist. But they didn't tell us you have to use a specific letter to stand for the number of years since 1985. So we can kind of choose a letter that makes us happy. I like to choose X. So X is going to be the number of years since 1985. Now we're going to write a linear model. So we're going to need two pieces of information, the number that repeats and the number that only occurred once. If I go back to the beginning of the problem, it tells me the chemist's salary was $35,000 in 1985 and increased by $300 per year. Because it says $300 per year, this is going to be the number that repeats. So every year, over and over and over again, I get an extra $300. Now, the one-time thing is the $35,000. That's my starting amount, and it doesn't repeat. I keep adding to that. So I only make $35,000 once, and then I keep adding after that. If I set up my equation, I would have S equals, the repeater number goes first, so $300, and it says per year. And since X is the number of years, I would multiply by X because that's how many times it repeats, plus my one-time amount, which is $35,000. And I would be done with that. I wrote an equation that models this situation. For number 3, Commonwealth Edison supplies electricity to residential customers for a monthly charge of $7.58 plus 0.8275 cents per kilowatt hour for up to 400 kilowatt hours. Write a linear model that relates the monthly charge C in dollars to the number of kilowatt hours used in a month. Now here it gives us two variables to use. The monthly charge is going to be C, and X is going to be the number of kilowatt hours used in a month. So it says here C, and we're going to write equals the monthly charge, and X is going to equal the number of kilowatt hours used in a month. So when we're talking about things that occur one time versus things that occur over and over again, we're saying within this month. So within this month, I'm going to pay this amount once, and I'm going to pay a different amount over and over and over and over again within the month. So if we go back to the beginning of the problem, it says we charge $7.58 plus 8275 per kilowatt hour. So here where it says 8275 per kilowatt hour, that's what tells me that it repeats because I'm paying it over and over and over again for every hour. And I'm only going to charge $7.58 one time within this month. I get that flat fee plus I pay extra per hour. So now if I write my equation, my charge will equal, now I repeated this per kilowatt hour. So that's the repeater, 0.8275. And since X is the number of kilowatt hours, I'm going to put an X here because it's per that amount. The X gets multiplied. Plus, I'm going to pay the $7.58 one time, so that goes at the end. All right, let's turn the page and take a look at another example. So these are some SAT style questions that we wanted to help you guys go over and practice so you're kind of prepared for the next time you take the PSAT. So it says here, Kathy is a repair technician for a phone company. Each week she receives a batch of phones that needs repairs. The number of phones she has left to fix at the end of each day can be estimated by the equation P equals 108 minus 23D, where P is the number of phones left and D is the number of days she has worked. What is the meaning of the value 108 in this equation? So let's start with this. If I find the number 108, which is what they're asking me about in the equation, it is a number that is not being multiplied by a variable. Now, because I know that the way that these equations are set up is that the number being multiplied by the variable, this is the repeater, and it's multiplied by a variable. Whereas B would be a one-time amount, which is not multiplied by a variable, so it's alone. Because the 108 is alone, I know that it's a one-time amount. Now, it's telling me also that this equation, P is the number of phones she has left, and D is the number of days she worked. So if I take this number and I subtract 23 phones per day, then this must have meant how many phones she started with. Because then if she fixes 23 phones per day, I'm going to keep subtracting that number from the amount she has left. So in part A, it says Kathy will complete the repairs within 108 days. I don't think that's the right answer. Kathy starts each week with 108 phones to fix. Well, that seems right. If she starts with 108 and she fixes 23 phones per day, then she's going to subtract that amount, and the number of phones she has left will be 108 minus the number of phones she fixes. So I'm going to say that option B is the correct answer here. A pediatrician uses the model H equals 3A plus 28.6 to estimate the height of a boy in inches in terms of the boy's age in years between the ages of 2 and 7. Based on the model, what is the estimated increase in inches of a boy's height each year? So the question says, what is the estimated increase of a boy's height each year? Now here where it says it's the increase, this is how much we are adding. Because increase means adding. So how much do we expect a boy to add every year? Because it's each year, it's going to repeat. So if I look at the equation, the number that I expect to repeat should be the number that's attached to the variable. So if I look here, 3 is the number that's attached to the variable, so 3 is the number that I expect to repeat, how much the boy is going to get added every year. Let's take a look at number 6. It says Mr. LePage spent $25,000 to buy a new truck for his construction business. He estimated the value of the truck after each of the next 5 years as shown in the table below. If the line passing through the points defined by the values in the table is graphed in the xy plane, which of the following is the best interpretation of the y-intercept in the context of the problem? All right, now y-intercept. When we went over what all these things stand for, we said that the y-intercept is the one-time amount. So it's how much you start with. So it says here that could the y-intercept be the number of years for which the value of the truck will decrease? Well, probably not, because the years are the x, not the y. The amount of the value of the truck is decreasing each year. Well, if it's decreasing each year, then that repeats. And the y-intercept should be a one-time thing. So I don't think that that's going to be the y-intercept. The value of the truck after the 6th year of ownership, I don't think it's going to tell me how much the value was after the 6th year, because it should tell me how much I started with. The value of the truck when it is new. Well, that makes sense, because that would be the one-time value that I started with. And then I'm going to keep changing that by continuously subtracting amounts. It's going to decrease every year. All right, so this is going to be the end of our examples, and we're going to practice this tomorrow in class. Thank you so much for watching, and have a great afternoon.